In this second video, we're going to continue with our quantitative chemistry to be able to calculate percentage yield, calculate the formula of a compound with a given data, and calculate the mass from a balanced chemical reaction, and use Avogadro's constant to calculate moles and grams. We'll be using many equations in these, so make sure you memorize these, but for the time being, here's a sheet that you could reference to be able to calculate moles, mass or molar ratio with an equation, percentage mass, the atomic ratio, the percentage yield, and the mass of an atom with the Avogadro constant we discussed. Percentage yield is important to calculate when you're doing your class experiments. This is because the percentage yield determines efficiency of a reaction. If a yield is 100%, it is the best to obtain. However, not all reactions can yield 100%, such as a few esterifications or reversible reactions. To calculate percentage yield, we must use the equation given to us. We use the actual yield divided by the theoretical yield, and then we times it by 100 to get our percentage. In this slide, we'll be calculating percentage yield with these two following equations. Use these equations in this question to be able to calculate the percentage yield of sodium bromide. Let's set this up in a table. So we have 4 grams of sodium bromide, and then we have 8 grams of hydrogen bromide given to us by the equation. Then we have the molar mass that we can find with our periodic tables. Once we have our mass divided by molar mass, which is from this given equation, we can calculate 0.1 moles of sodium bromide and sodium hydroxide and hydrogen bromide. Because it's a 1-to-1 ratio or a 1-to-1 stoichiometry, we have 0.1 moles of sodium bromide. The molar mass of sodium bromide is 103, therefore 0.1 times 103 is equal to 10.3 grams of sodium bromide. Now that we have our theoretical yield, we can take our actual yield, 8.3 grams of sodium bromide, and divide it by 10.3, the theoretical yield, times by 100 to get 80.6 percentage yield. We could also do this with moles. Sorry, this should be moles, not grams. So we convert 8.3 grams of sodium bromide divided by 103 to get 0.0806 moles of the actual sodium bromide. Then once we divide it by the theoretical 0.1 mole and times by 100, we get the similar percentage yield, showing that we could do this through moles and grams. Chemical formula indicates the number of each element in a compound, whilst the empirical formula gives us the simplest ratio of the elements from a given compound. Pause the video and try this. A good hint is to use the percentages as you would mass. For example, 71% is divided by 107.9 to give us 0.66 moles. We do the same for carbon and oxygen, and then we see we have a ratio of moles 0.66 to 0.66 to 1.32. What we can do here is divide by the smallest number, 0.66, giving us the stoichiometry of the moles of 1 silver, 1 carbon, and 2 oxygens. Therefore, the empirical formula would be AgCO2. 1 mole is the amount of substance that contains the same number of particles as atoms in 12 grams of carbon-12. Avogadro's constant, 6.0 times 10 to the 23, can be used in this equation as a constant to find the amount of substance with the unit moles. By doing the number of particles divided by Avogadro's constant, we can find this. So to calculate the number of oxygen atoms in 0.5 moles of oxygen molecule, O2, we have to do 2 oxygen molecules times 0.5 times 6.022 times 10 to the 23 to get 6.022 times 10 to the 23. This is Avogadro's constant. Double check this by yourselves on your calculator. To continue to calculate the mass of atoms, we do the atomic ratio of an element divided by 6.022 times 10 to the 23. To calculate the mass of boron with the atomic ratio of 10.81 to the second decimal place, the mass of boron will be equal to the atomic ratio of element boron 10.81 divided by Avogadro's constant 6.022 times 10 to the 23, which is equal to 1.8 times 10 to the minus 23 grams. Also check this out yourselves.